Tonight, something that holds every galaxy apart is losing its grip. A telescope in the Arizona desert just measured the push that drives the universe outward, and for the first time in 25 years, the number dropped. Dark energy, the invisible force that fills 70% of everything that exists, is not steady, it is fading. We will follow the signal across 8 billion years of cosmic history, a machine with 5,000 robot eyes tracking galaxies no human has ever mapped. The moment a fixed law turned into a ticking clock, and what happens to every star in the sky when the force holding them apart starts to let go. If deep space amazes you, hit like and subscribe. Close your eyes if you want. We begin. Look up tonight. Every star you see is drifting away from you. Not because it wants to, because something is pushing it. And that push, the one scientists spent a quarter of a century calling a constant, just turned out to be anything but. To understand what broke, you need to understand what we thought we knew. And to understand that, you need to go back to a time when nobody even realized the sky was moving. For most of history, the stars looked nailed in place. Same shapes your grandparents saw, same shapes the ancient Greeks sketched into pictures of hunters and bears. Steady, quiet, permanent, that picture was a lie. In the 1920s, an astronomer named Edwin Hubble pointed a telescope at the faint smudges between the stars and proved something that changed everything. Those smudges were not clouds. Each one was a whole galaxy, a city of billions of suns sitting so far away that your brain cannot hold the distance. Picture finding out that every speck of dust on your bedroom floor is actually a packed stadium full of burning stars. That was the size of the shock. But the shock got worse. When Hubble measured the light coming from those galaxies, he noticed something strange. Almost all of it was stretched toward the red end of the rainbow. Light does that when the thing giving it off is moving away from you. Think of a siren on an ambulance as it races past your house. The pitch drops as it speeds away. Galaxy light does the same trick, only with color instead of sound. So, the galaxies were running. Every direction Hubble looked, they fled, and here is the part that messes with your head. They were not running away from one center, like sparks flying off a campfire. They were all spreading apart from each other, everywhere, all at once. The whole stage was getting bigger. Think of a balloon with dots drawn on it. Blow it up, and every dot drifts away from every other dot. No dot is the middle. No dot stays still. The rubber between them just keeps stretching. That rubber is space itself. And you are one of the dots, watching all the others slide away. This was the first crack in the old story. The universe was not a calm, finished room. It was a thing that was happening, expanding, moving, alive in a way nobody had imagined. For a while, scientists made peace with it. Fine, they said. The universe is growing. It exploded into being a long time ago and has been coasting outward ever since. Like a ball tossed straight up into the air, still rising, but slowing down. Gravity from all that matter should be pulling everything back, tapping the brakes on the whole show. That made sense. It felt right. The expansion was real, but gravity was the boss, and gravity always wins in the end. Or so they thought. The only question left seemed simple. Would the brakes stop the universe gently, like a car rolling to a halt on a flat road? Or would gravity yank everything back into one giant pile-up someday? Scientists built better telescopes to find out. They aimed them at the oldest, faintest light they could catch, hoping to measure exactly how fast the cosmos was slowing down. In 1998, they got their answer. It was the opposite of everything they expected. And it came from stars that were already dead. To check the speed of the universe, scientists needed a special kind of lighthouse. A flash so bright and so regular that they could spot it across unthinkable distances and know exactly how far away it sat. They found it in dying stars. When a certain type of white dwarf star pulls too much gas from a partner star and crosses a weight limit, it explodes. Every time, the blast shines with nearly the same brightness. Think of a light bulb that always burns at the exact same wattage no matter where you plug it in. If you know how bright it truly is, and you measure how dim it looks from where you stand, the gap tells you the distance. A candle across your living room looks bright. The same candle a mile down the road looks like a pinprick. Same flame, different glow. Easy math. Two rival teams were racing to use these explosions in the 1990s. One was the Supernova Cosmology Project, based out of a lab in California. The other was the High Z Supernova Search Team, spread across universities in 3 countries. They did not share data, they did not share methods. They barely spoke. Each team believed they would be the one to measure how fast the universe was hitting the brakes. That was the prize. The first group to pin down the deceleration rate would make history. Their names would go into every textbook printed for the next 100 years. Their plan was simple. Find the most distant exploding stars they could, compare them to closer ones, and measure how much the brakes had kicked in over billions of years. The faraway explosions were supposed to look a little too bright. That would mean those galaxies were closer than expected, which would mean the expansion had been losing steam all along. Nice and neat. Gravity wins in the end. The light came in. The teams crunched the numbers. The distant stars were too dim. Not a little dim. Clearly, stubbornly, impossibly dim. The galaxies were farther away than they should have been. The only way that made sense was if the universe had not been slowing down at all. It had been speeding up, like a car flooring the gas pedal on an empty highway with nobody touching the wheel. The expansion was getting faster, not slower. Every year the gap between galaxies grew a little wider, a little quicker. Both teams stared at the same result. They tore their own work apart looking for a mistake. There was dust to worry about, faint dust between galaxies that could dim light and fake the whole thing. They hunted for it. They ruled it out. The answer would not go away. One of the lead scientists later said he was sure he had made an error, because the result felt too strange to be real. He spent 3 weeks trying to prove himself wrong. He ran the numbers on different computers. He had colleagues check every step. The numbers would not budge. A speeding up universe meant something was pushing outward harder than gravity could pull. Something invisible. Something with no name. Something nobody had asked for. Both rival teams published in the same year. They had been trying to beat each other, and instead, they handed the world the same news. The universe is not coasting to a stop. It is accelerating. A force was loose in the cosmos, fighting gravity and winning, stretching space faster and faster across distances so wide that light takes billions of years to cross them. Nobody had the faintest idea what it was. They could measure it. They could prove it was there. They just could not see it, touch it, or explain it. So they gave the mystery a name. They called it dark energy. The name is almost a confession. Dark, because it gives off no light, no heat, no glow of any kind. Energy, because something is clearly doing work, shoving galaxies apart with a strength that beats gravity across the whole sky. Put those 2 words together and you get a label that says, we know it is there and we have no clue what it is. Here is the fact that should stop you cold. This stuff you cannot see, cannot feel, and cannot catch is the main ingredient of the entire universe. It makes up around 70% of everything that exists. 7 out of every 10 parts of reality is this invisible push. Sit with that for a second. Every star you have ever seen, every planet, every galaxy in every photograph you have scrolled past, all of it together is the small slice. The mystery force is the big slice. You have been looking at the universe your whole life and somehow missed the part that runs the place. Picture a giant glass jar that holds everything in existence. Fill 70% of it with a clear liquid you cannot see or smell or touch. Then sprinkle in a few grains of glitter scattered thin. The glitter is every galaxy, every sun, every world. The invisible liquid is dark energy. And it is pushing the walls of the jar outward, making the whole thing bigger every second. What makes dark energy so unsettling is how it behaves backward from everything else you know. Normal stuff pulls. Gravity grabs. Two objects with mass drift toward each other the way your coffee mug slides toward the edge of a tilted table. The more matter you pile up, the harder it all yanks inward. Dark energy does the opposite. It pushes. It pries things apart. And here is the strange part. It does not weaken as the universe grows. A campfire fades as you walk away from it. A speaker gets quieter down the hall. Dark energy refuses to follow that rule. As space stretches and new gaps appear between galaxies, the push stays just as strong, filling every new inch the moment it opens. That means the universe is locked in a tug of war. Gravity pulling all the matter back together, dark energy trying to rip it all apart. For the first several billion years, matter was packed tight, so gravity was winning, slowing the expansion down. Then space spread out enough that matter thinned. Gravity loosened its hold, and dark energy took over the fight for good. You are living in the era when the push is beating the pull. That is why the galaxies are speeding up instead of slowing down. The invisible giant grabbed the wheel, and here is the twist that makes this story feel like it was written by someone with a cruel sense of humour. The idea of a push built into empty space was not new in 1998. It was over 80 years old, and the man who invented it threw it in the trash and called it his biggest mistake. Go back to 1917. Albert Einstein had just finished the work that made him a legend. His theory of gravity described how heavy objects bend space and time, the way a bowling ball dips a mattress and smaller things roll toward the curve. The math was beautiful. Then he pointed it at the whole universe, and it told him something he did not want to hear. His own equation said the universe could not sit still. All that matter pulling on itself through gravity meant the cosmos should be collapsing inward or flying apart. Either way, it could not just hang there, calm and fixed. But in 1917, everyone, Einstein included, believed the universe was exactly that. Calm, fixed, eternal, so Einstein did something unusual for a genius. He flinched. He added a small extra term to his equations by hand, a gentle outward push, just strong enough to balance gravity and hold everything frozen. He called it the cosmological constant. It was a patch, a fudge factor to make the math match what he expected. Then Hubble proved the galaxies were flying apart. Einstein's raw equations had predicted that before he taped them down. If he had trusted his own math, he could have predicted the expanding universe years before anyone saw it. He pulled the constant out, threw it away, and reportedly called it the biggest blunder of his life. For decades, the cosmological constant was a punchline, a famous mistake from a famous mind. Textbooks mentioned it the way you mention a bad haircut from high school. It was dead, buried, laughed off. Then 1998 arrived, and the very thing Einstein invented, erased and regretted came crawling back wearing a brand new name. The math term for a push built into empty space already existed. Einstein had written it. The cosmological constant, resurrected, became the simplest explanation for dark energy, a fixed pressure woven into the fabric of space itself. The blunder was not a blunder, it was an accidental prophecy. The grip felt permanent. Scientists measured it, named it, filed it away, and moved on. For 25 years, nobody seriously questioned whether the push would stay the same. It was written into the equations as a fixed number, a constant, the very backbone of every model of the cosmos you have ever heard of. The grip was not questioned, it was trusted, and trust in science is a dangerous word. But in the Arizona desert, a machine was about to prove that the push everyone depended on was already slipping, and the number that held modern physics together was about to move. The instrument that caught it does not look like a telescope. It looks like a metal flower with 5,000 petals, and each petal is a tiny robot. It sits on top of a mountain called Kitt Peak in the Arizona desert, bolted to a telescope that has been scanning the sky since the 1970s. The telescope is called the Male, named after an astronomer most people have never heard of. The dome is white, round and quiet during the day. At night, it opens like a giant eye. But the real story is the device riding inside it, something built for one purpose, and one purpose only: to map the exact position of millions of galaxies in 3 dimensions, stretching back across billions of years of cosmic time. Its name is DESI. The Dark Energy Spectroscopic Instrument. It took over a decade to design, years to build, and a small army of engineers, physicists, and technicians working across 3 continents to put together. And the way it works is unlike anything you have seen before. Imagine standing in a dark field at night, surrounded by fireflies, thousands of them, scattered in every direction. Each firefly is a galaxy. You want to know how far away each one sits, how fast it is moving, and whether the space between them is stretching at a steady rate or changing. But you cannot walk over and measure. You can only read the light. So you build a machine that sends out 5,000 tiny arms, and each arm points at a different firefly and catches its glow. Each arm feeds that glow through a glass fibre thinner than a human hair, down into a room below where the light gets split into a rainbow. And in that rainbow, you can read the galaxy's speed, its distance, and the stretch of the space it sits in. All 5,000 at once. Every 20 minutes, the arms swing to a new batch. By morning, tens of thousands of galaxies have been logged. That is DESI. 5,000 robot eyes, each one locking onto a galaxy, reading its light, and moving on to the next. Night after night after night. The people who keep DESI running work in near darkness. The dome stays cold, sometimes close to freezing, even in the desert. They move in silence, because any vibration, a drop tool, a heavy step, can throw off a fibre thinner than a thread on your pillow. One misalignment and a galaxy's light lands on the wrong sensor, and a data point covering 1 billion years of history becomes noise. They check thousands of fibres every single night. Adjusting, realigning, confirming. It is tedious, precise, invisible work. And it matters more than almost anyone outside that mountain will ever know. What DESI is hunting for is hidden in the pattern of how galaxies are spread across the sky. Not just where they sit right now, but where they sat billions of years ago. Because light takes time to travel, looking far away is the same as looking back in time. A galaxy 10 billion light years from your window is showing you what it looked like 10 billion years ago. You are not seeing the present, you are seeing a memory. And the deeper DESI looks, the older the memories get. Some of the galaxies in its map are so far away that their light left home before the Earth even existed. Before the sun lit up. Before our corner of the Milky Way was anything more than a cold cloud of gas. That light has been travelling toward you for longer than our entire solar system has been alive. So when DESI maps millions of galaxies at different distances, it is building a timeline, a record of how the universe expanded, decade by decade, era by era, going back almost to the beginning. Think of it like slicing through the trunk of an ancient tree and reading the rings. Each ring tells you what that year looked like. Each layer of DESI's map tells you how fast the universe was stretching at that age. And buried in that timeline is a fingerprint, a pattern left behind by sound waves that rippled through the infant universe about 380,000 years after the Big Bang. Back then, the cosmos was a hot, dense soup, hotter than any oven you can picture. Sound waves rolled through it like ripples through water in a bathtub. Then the universe cooled. The soup hardened. And the ripples froze in place. Picture dropping a stone into a perfectly still lake. Rings spread outward. Now imagine the entire lake turning to ice in one instant, trapping every ring exactly where it was. That is what happened to the early universe. The sound waves became frozen ripples in the arrangement of matter. And billions of years later, galaxies formed along those ridges, like towns built on the high ground of an ancient flood. Scientists call these frozen ripples baryon acoustic oscillations. You do not need to remember that name. What matters is that each ripple has a known size, about 490 million light-years across. That is your ruler. A measuring stick baked into the universe at birth, the same size everywhere, the same size at every age. Now here is how you use it. Imagine you know that a particular coin is exactly 1 inch wide. If you hold it close to your face, it looks big. Set it across the room, it looks small. Set it a mile away, and it is a speck. But in every case, you know the real size. So the way it looks tells you the distance. That is what DESI does with the frozen ripples. It finds the pattern in the galaxy map at different ages. It measures how wide the ripple appears. Then it works backward to figure out how much space has expanded between that moment and now. Do this for dozens of different eras, stacking them like layers in a core sample, drilled from deep time, and you build the most detailed expansion record ever assembled. This is what DEDI was built to do. Read the ruler at every age it could reach, build a timeline of the expansion stretching back 8 billion years, and check whether dark energy, the invisible push behind all of it, has stayed the same across the ages, or whether the grip has been changing all along. In April 2024, the first major results came out. The team had mapped over 6 million galaxies spread across 8 billion years of time. It was the largest three-dimensional map of the universe ever made. If you could print it out, it would fill a room the size of a warehouse, every dot a galaxy, every gap a stretch of expanding space. And the expansion history it revealed did not match the one every textbook had been printing for 2 decades. The team did not celebrate when the numbers came in. They went quiet. One of the senior researchers later described the moment as the opposite of excitement. It was dread. Because if the result was real, it meant the foundation of modern cosmology had a crack in it. And if it was an error, it meant something was wrong with the most expensive instrument they had ever built. Neither option was comforting. They ran the analysis again. Different software, different assumptions, different team members checking each step. The result did not change. The push was not steady. It was weaker now than it was billions of years ago. The number that had been treated as a constant, the backbone of the entire standard model of the cosmos, appeared to be drifting. Not by a wild amount. The signal was subtle, like watching the hour hand of a clock and noticing it is running a fraction of a second slow every day. Most people would never notice. Your eyes would skip right past it. But DESI's instruments were built to catch exactly this kind of whisper. And they caught it. Then the team did something careful and brave. They checked their result against older, completely separate datasets. Supernova measurements from the 1990s. Temperature maps from the afterglow of the Big Bang itself. If the drift was a glitch in DESI's pipeline, it would vanish when compared to other sources. It did not vanish. The drift held. Stay with me here, because what they found when they looked at the oldest light was not what any model predicted. Dark energy's grip on the universe, the force you were told would push forever at the same strength, was loosening. Not fast. Not in a way you would feel in your bones or see in the sky tomorrow night. But across billions of years, the push had changed. The constant was not constant. Think about what that means for a second. Every model of the universe built in the last 25 years rests on the idea that dark energy does not change. Every simulation, every forecast, every prediction about what happens to the stars a trillion years from now, all of it assumes a fixed push. If the push is changing, those predictions are wrong. Not slightly wrong, fundamentally wrong, like building a house on what you thought was bedrock and finding out it is sand. The first results were strange. The second batch, released months later with more galaxies and tighter measurements, was stranger. Then a completely different team stepped in. Different instrument, different continent. They checked the same patch of sky and found the same drift. The word coincidence stopped being an option. Something was happening to the force that runs the universe. Something quiet, slow, and deep. And nobody had a backup plan for what comes next. Here is the part that should unsettle you. The number that held modern physics together for a quarter century was never explained. Not once. Nobody knows what dark energy is. Nobody knows where it comes from. And now, the one thing scientists thought they could say about it with confidence, that it is constant, turns out to be wrong too. To understand how deep this crack goes, you need to see the hole that was already there before Deci pulled the thread. Because the truth is, dark energy was always standing on shaky ground. Scientists just agreed not to look down. Start with the simplest version of the story. If dark energy is a property of empty space, then quantum physics should be able to predict how much of it there is. The idea sounds reasonable. Particles pop in and out of existence everywhere all the time, even in what looks like a perfect vacuum. You cannot see them. They flicker in and vanish faster than a blink. But they carry energy. And that energy adds up. So physicists sat down and did the math. They calculated how much energy the vacuum of space should hold, based on everything they knew about quantum mechanics. They followed the rules carefully. They double-checked the equations. They got a number. Then they compared it to the actual measured amount of dark energy in the universe. The two numbers did not match. They did not miss by a factor of 2. Not 10. Not 1,000,000. Not 1,000,000,000. The predicted number was too big by a factor of 10 followed by 120 zeros. Written out, that is a 1 with 120 zeros after it. That is not a rounding error. That is not a near miss. That is the single worst prediction in the entire history of physics. No other field of science has ever been this wrong about anything. Picture this. You ask your kitchen scale how much a bag of sugar weighs. It says the bag is heavier than every star, every planet, every galaxy, and every atom in the entire observable universe combined. Times 1,000,000,000,000. Times another 1,000,000,000,000. That is the gap between what quantum theory predicts and what astronomers actually measure. For decades, physicists just shrugged and moved on. They called it the vacuum catastrophe. They wrote papers about it. They argued at conferences. They proposed theories and shot them down. And then they quietly agreed to treat the measured value as the correct one and never ask too many questions about why the math was so absurdly, spectacularly wrong. That is not science at its bravest moment. That is science sweeping something enormous under the rug, because nobody knew what else to do. And here is the thing about rugs. They do not care how big the thing underneath is. They just hold the shape until someone steps on it. Think about it this way. You have two pillars of modern physics. One is quantum mechanics, the science of the very small. Atoms, electrons, the particles that make up everything you touch. Quantum mechanics works. It is the most precisely tested theory in history. The predictions it makes are accurate to more decimal places than you could fit on a chalkboard. The other pillar is general relativity, the science of the very large. Gravity, space-time, the curves and bends that shape the cosmos. General relativity works too. It predicted black holes, gravitational waves, and the bending of light around massive objects, all confirmed by experiments. Two pillars, both strong, both tested, both trusted by every physicist alive. And when you point them at the same question, what is the energy of empty space, they give you answers that disagree by 120 zeros. That is not a crack in one theory. That is a canyon between the two biggest ideas in physics. And dark energy sits right in the middle of that canyon, waving at both sides, belonging to neither. Here is why that matters to you right now. The shrug only works if dark energy behaves itself. If it sits there steady and quiet, doing the same thing century after century, then fine. You can treat it like a fixed number in your equations. You plug it in. You build everything else on top. The building stands. That is exactly what cosmologists did. They took the measured value, plugged it into the standard model of the universe, and called it the cosmological constant. Lambda, a single Greek letter that carries the weight of 70% of all reality on its shoulders. The whole framework built around it is called Lambda CDM. Lambda for dark energy, CDM for cold dark matter, the invisible stuff that holds galaxies together like glue. Together, these two mysterious ingredients explained almost everything astronomers could see. The expansion rate, the way galaxies cluster across the sky, the temperature pattern in the oldest light ever captured. All of it clicked into place. For 25 years, Lambda CDM was the champion. The winner. The model every simulation ran on, every paper assumed, every graduate student memorized for their exams. Careers were built on it. Telescopes were designed around it. Billion-dollar missions were launched to refine its numbers. A cosmologist at Princeton described it in a 2024 interview. She said she had spent her entire career studying a universe that expanded forever. That was the world she knew. The world her equations described. If the new data held up, she would not just have to redo her math. She would have to rebuild her intuition. Everything she had built her understanding of reality on was suddenly a question mark. And its single most important assumption, the one brick holding the entire arch together, was that lambda does not change. Now Desi is saying it does. If lambda is not constant, the whole framework wobbles, not crashes overnight. Wobbles the way a table wobbles when you realize one of its legs is a fraction of an inch too short. Everything on top still sits there, but you stop trusting it to hold your weight. Think about what that means for you. Every documentary you have ever watched about the fate of the universe was built on lambda being fixed. Every article that told you the cosmos will expand forever. Every teacher who said the stars will slowly drift apart until everything goes dark. All of it assumed the push never changes. If lambda changes, those endings change too. The story you were told about where everything is heading may not be the right story at all. Two camps formed among physicists, and they could not be more different. The first camp said, stop panicking. Maybe the cosmological constant is fine, and Deji's signal is just noise. A statistical flicker that looks exciting now, but will vanish when more data comes in. Be patient, they said. Do not burn down the house because one thermometer reads funny. The second camp pointed at the vacuum catastrophe. A 120-0 mismatch is not a small clue, they argued. It is an alarm that has been screaming for decades. And now Duddy is handing us a second alarm from a completely different direction. Maybe, just maybe, the constant was never supposed to be constant in the first place. Maybe dark energy is alive. Moving, changing with time. This idea has a name. Quintessence. The word comes from ancient philosophy. A fifth element. Something beyond earth, water, fire, and air. The ancients believed there had to be a substance that filled the heavens, something pure and unchanging that made the stars different from the dirt. They were wrong about the details. But the instinct that there is something filling the emptiness turns out to be closer to truth than they could have imagined. In modern physics, quintessence is a slow-rolling energy field that fills all of space. Think of it like a fog that drifts across a valley. Sometimes the fog is thick and you can barely see your hand. Sometimes it thins and the shapes of the hills emerge. Sometimes it nearly vanishes altogether. Unlike a constant, quintessence has a personality. It has a past that looked different from its present. It has moods. Here is another way to picture it. A constant is like a light switch locked in the on position. It does not care what time it is. It does not care what the universe looks like. It just pushes, the same way forever. Quintessence is more like a candle. It burns, it flickers. The flame changes shape with every passing hour. And eventually, if you watch long enough, the wax runs out. If quintessence is real, dark energy is not a fixed feature of the cosmos. It is a living force with a history, a direction, and a destination that no equation on Earth can pin down yet. There is a number physicists use to test this idea. They call it W. You do not need to memorize it, but you need to understand what it does, because this single letter is now the most watched number in all of physics. Think of W as a dial on a dashboard. The dial has a mark at -1. If the needle sits exactly on that mark, dark energy is a perfect constant. Steady, unchanging, the lambda everyone trusted for 25 years. The safe answer. The boring answer. The answer that lets you sleep at night. If the needle sits anywhere else, even a fraction to the left or right of -1, dark energy is not constant. It is dynamic. It is moving. It has a direction. And that direction determines the fate of everything. A value above -1 means dark energy is weakening. The push is getting softer. Gravity might eventually win. A value below -1 means something far more dangerous. It means the push is getting stronger over time. Phantom energy territory. The Big Rip scenario. DESI's data puts the needle just slightly above -1, not by much. The drift is small, like watching a thermometer creep up by 1/10 of a degree over a decade. Most people would never notice, but cosmologists noticed, because in a universe governed by a single number, 1/10 of a degree is the difference between an eternal slow fade and a total collapse. The grip was always shaky. We just never had a machine sharp enough to feel it slip. Think about Einstein for a moment. In 1917, he invented a fudge factor to hold the universe still. He later ripped it out and called it a mistake. Then, the universe brought it back in 1998 and made it the most important number in cosmology. Now a machine in the desert is saying that number is drifting. The man's invention has come back to haunt physics 3 separate times. Each return brought worse news than the last. You have to wonder what he would say if he could see this. The constant he created, killed and resurrected by accident is now breaking apart for a 3rd time. That is not a coincidence. That is the universe telling us something we have been refusing to hear. Sit with that for a second. The force that fills 70% of everything that exists might be dying. It fills the space between your hand and this screen. It fills the gap between one atom in your body and the next. And it is fading, letting go. Nobody knows what happens when it finishes. If dark energy is fading, every prediction about the future of the universe falls apart. Every single one. And what replaces them is not comforting. Nobody in physics wants to answer the next question. You can hear it in the way they talk at conferences. The pauses before they respond, the careful hedging, the phrases like it is too early to speculate and we need more data. All of it is code for one thing. They are afraid of the answer. But the question will not go away, because it is the only one that matters now. What happens to the universe if dark energy stops pushing? For 25 years, the answer was simple and final. Dark energy is constant. The push never stops. The universe expands forever. Galaxies drift apart. Stars burn out one by one. Over trillions of years, the cosmos grows darker, colder, emptier, stretching toward a quiet death that physicists call the heat death of the universe. Picture a campfire at the end of a long night. The flames die down. The embers glow. Then the glow fades. Then there is nothing but cold ash spread across the ground, growing colder with every passing hour. That is the heat death. The universe's cold ash. No light, no heat, no motion, no change, just silence. Forever that was the forecast. Grim but stable. A slow fade into endless cold. At least you could wrap your head around it. At least the math was clear. At least every physicist on Earth agreed on the ending, even if none of them liked it. There was even a strange comfort in it. If the universe was going to die, at least it would die quietly. No explosion, no scream. Just a whisper that got softer and softer until there was nothing left to whisper. But that comfort depended on dark energy being constant. Remove the constant, and the quiet ending vanishes with it. The forecast does not just change, it shatters into pieces, and each piece points in a different direction. And the new possibilities are not gentle. Start with the first scenario. If dark energy is fading, weakening slowly over billions of years, then at some point the push drops below the pull. Gravity wins the tug of war. The expansion slows, stops, and reverses. Everything that has been drifting apart begins falling back together. Slowly at first, so slowly that for billions of years nobody would notice. Then faster. Galaxies that spent eons fleeing each other start drifting inward. The space between them shrinks. The temperature rises. Stars that were born in the cold quiet of a spreading universe find themselves in a cosmos that is heating up and squeezing tighter every century. Picture the balloon from earlier, the one with dots drawn on it, but now run it in reverse. Stop blowing. The rubber contracts. The dots slide toward each other, faster and faster, until every dot meets in the middle. Physicists call this the Big Crunch. A mirror of the Big Bang. The universe born in an explosion of expansion, ending in an implosion of collapse. The final moments of a Big Crunch universe would be almost too strange to describe. The sky would no longer be dark. As galaxies piled closer, the night sky would glow with starlight from every direction. The background radiation of the cosmos, the cold whisper left over from the Big Bang, would heat up as space compressed. Your sky would go from black to red to white. And in the final fraction of a second, everything collapses. Every atom, every galaxy, every photon of light, all of it forced back into a single point so dense that the laws of physics break down completely. You came from that point. The atoms in your hands right now, the iron in your blood, the calcium in your bones, all of it was forged in the first moments after the Big Bang. If the Big Crunch is real, those atoms go back. All of them. Everything you have ever touched, seen, or dreamed about, compressed into a space smaller than the period at the end of this sentence. Option 1. It is brutal. But at least it is an ending you can picture. Option 2 is worse. What if dark energy does not just fade? What if it changes direction? What if the push becomes a pull, and then the pull gets stronger, and there is no limit to how strong it gets? This idea is called phantom energy, and it leads to the most violent ending the cosmos could face. In a phantom energy universe, the force that is currently spreading galaxies apart begins tearing at everything. First, it separates galaxy clusters from each other. Then it pulls individual galaxies apart. Then solar systems. Then planets from their stars. And it does not stop there. Think of tearing a sheet of paper. First, the edges pull apart. Then the middle rips. Then every fibre splits. Then the fibres split again, and again until there is nothing left but dust. And then the dust rips too. That is the Big Rip. Every structure in the universe, from the largest galaxy cluster to the smallest atom, torn apart by a force that keeps growing until nothing holds together anymore. The fabric of space itself comes undone. The terrifying part is the timeline. For most of a Big Rip universe, everything looks normal. Billions of years pass with nothing unusual. The galaxies drift the same way they always have. Stars are born and die. Planets orbit. If you were alive in the early stages, you would never know what was coming. Then, about 1 billion years before the end, the distances between galaxy clusters start growing faster than expected. Astronomers would notice, they would run the numbers, and the numbers would tell them the expansion was accelerating in a way that had no brakes. 60 million years before the end, the Milky Way itself starts coming apart. Stars at the edges drift away first, then the middle loosens. The galaxy that held together for billions of years begins to dissolve like sugar in hot water. 3 months before the end, your solar system unbuckles. The planets drift away from the sun. The orbits that held for 4.5 billion years simply stop working. 30 minutes before the end, the Earth comes apart. The ground beneath your feet splits. The oceans scatter. And in the final fraction of a second, the atoms in your body are pulled apart faster than light. Nobody wants this to be real. But the math allows it, and if dark energy is changing, phantom energy sits right there on the table, next to every other option. There is a third possibility, maybe the strangest one of all. What if dark energy does not fade smoothly in one direction? What if it oscillates, gets weaker, then stronger, then weaker again, like a heartbeat so slow it takes billions of years between beats? In this picture, the universe breathes. It expands for an era, slows down, speeds up again. Never quite collapsing, never quite tearing itself apart, just pulsing. Alive in a way nobody expected. A cosmos with no final page. Picture your own chest. You breathe in, your lungs fill. Then you breathe out, the air leaves, and then, without thinking, you breathe in again. You have been doing this since the moment you were born. You have never decided to start or stop. It just happens. Now imagine the whole universe running on the same rhythm, only each breath takes billions of years. Your era, the one you are living in right now, would be just one breath in an infinite sequence. Not the ending, not the beginning. A single inhale in a rhythm that has no start and no finish. There may have been a universe before yours that collapsed and bounced back. There may be one after yours that does the same. You would never know. You are inside one breath, looking out, and the next breath has not come yet. Here is what matters about all three options. None of them are impossible. None of them are confirmed, and the instruments we have right now cannot tell them apart. We can see that the push is changing. We cannot see where it is heading, like watching a river bend without knowing whether it leads to a waterfall, a calm lake, or back to where it started. Let us be clear about the timescale. None of these scenarios happen tomorrow. Not in your lifetime, not in your children's lifetime, not even in the lifetime of your species. We are talking about spans of time so long that the sun will burn out and the earth will go cold long before any of these endings arrive. Your morning coffee is safe. Your evening walk is safe. The stars above your head tonight will burn for billions of years before any of this matters. But the physics changes right now. Today, the equations that describe the universe need new inputs. The simulations that predict the future need new rules. The story that textbooks have been telling about how everything ends needs to be erased and rewritten from the first line. And the scientists doing the rewriting do not yet have an ending to put in. They have options. They have fears. They have instruments sharp enough to see that something is changing. But the page where the answer should go is still blank. If you are still here, you belong here. Subscribe if you want to keep going deeper. But here is the thing that keeps cosmologists up at night. The scariest part is not the future. It is the past. Scientists use the same DESI data to look backward in time. Past the drift, past the fading. All the way back to the young universe. And what they found there makes the future question almost beside the point. Because the push was not always this weak. It used to be stronger. Much stronger. And that changes the origin story, not just the ending. This is where the story bends in a direction nobody saw coming. Because the real shock is not that dark energy is fading now. The real shock is that it has been fading for a very, very long time. Billions of years. Slowly losing power while nobody was paying attention. And the implications of that reach far beyond what happens in the future. They reach backward, into the history of everything. When scientists used the DESI data to look backward instead of forward, they expected to see dark energy sitting at the same level across every era. That is what a constant does. It does not care whether the universe is young or old, hot or cold, packed tight or spread thin. A constant just pushes. Same strength, same direction, forever. The DESI team had already seen the drift in the recent data. Dark energy weakening over the last few billion years. That alone was enough to shake the field. But the real test was deeper. They needed to check the ancient data. Galaxies so far away that their light had been travelling for 7 or 8 billion years before reaching the detector. If dark energy was truly constant, those ancient galaxies would show the same push strength as the nearby ones. Clean, flat, boring, the kind of result that lets everyone go home and keep using the same equations. The ancient data did not cooperate. In the early universe, when everything was closer together and hotter than any oven you could build, dark energy appears to have been stronger. Not slightly stronger, measurably stronger. The push was harder billions of years ago than it is tonight. This is not what anyone expected. Not the engineers who built DESI, not the theorists who wrote the equations it was designed to test, not even the skeptics who were already suspicious of the cosmological constant. A fading dark energy is strange, but a dark energy that started strong and has been bleeding power ever since is something else entirely. That changes the whole story, not just the ending, the beginning. Think about what a stronger early push means. If dark energy was shoving harder in the first few billion years, then gravity had to fight a fiercer headwind when it tried to pull matter together. Every galaxy you see tonight exists because gravity managed to gather enough gas and dust into one spot, despite the push trying to spread it all apart. If the push was stronger back then, that victory was narrower than anyone realized. Gravity barely won. You are the proof. The atoms in your body clump together in stars that should not have formed as easily as we thought. A slightly stronger early push, and the universe would have been a thin, even fog. No clumps, no stars, no planets, no you. Picture a gardener trying to plant seeds in a windstorm. The harder the wind blows, the fewer seeds take root. Early dark energy was that wind. And the fact that anything grew at all tells you something about how fierce the fight was. There is another consequence you probably have not considered: the first stars. If the push was stronger in the early universe, the gas clouds that would eventually collapse into the first generation of stars had to fight harder to pull together. That means the first stars may have formed later than our current models predict, or in different numbers, or in different sizes. The first stars matter because they are the factories. They forged the heavier elements, the carbon, oxygen and iron, that eventually ended up in planets, in oceans, and in you. If those factories started late or ran differently because dark energy was pushing harder than expected, the whole supply chain that led to you sitting here tonight shifts. The recipe stays the same, but the timing changes. And in a universe where timing is everything, that shift matters. A few 100 million years earlier or later could mean the difference between a cosmos full of rocky planets and one with almost none. It also changes how the universe cooled. The expansion rate controls the cooling rate. A faster expansion stretches space more quickly, which drops the temperature more quickly. If dark energy was stronger early on, the cosmos cooled on a different schedule than our models assume. The temperature history of the universe matters more than you might think. It determines when the first atoms formed, when the first light escaped, when the first stars ignited. If the cooling happened faster or slower than we calculated, every milestone in the cosmic timeline shifts. The universe you know, the one described in every science documentary you have ever watched, has its timing slightly wrong. And it may solve a problem that has been haunting cosmology for over a decade. You might have heard of the Hubble tension. If you have not, here is what you need to know. Scientists have two ways of measuring how fast the universe is expanding right now. Two methods. Both careful, both precise. Both checked and rechecked by teams that do not even like each other. The first method looks at the afterglow of the Big Bang, the oldest light in the cosmos. It reads the pattern in that ancient glow and works forward to predict today's expansion rate. The second method skips the old light entirely. It looks at nearby galaxies, measures their speed directly using exploding stars as mile markers, and calculates the rate from the ground up. Both methods should give the same answer. They do not. The gap is small, but stubborn, like asking two people to measure the length of your kitchen table. One says 72 inches, the other says 74. Neither made a mistake. Their rulers are fine, their technique is clean, but the numbers refuse to agree, no matter how many times they remeasure. At first everyone assumed someone had made an error. Maybe the ancient light method was slightly off. Maybe the nearby galaxy method had a calibration problem. Teams went back and rechecked everything. They swapped instruments. They redid calculations from scratch. They had rival groups verify each other's work. The gap did not close. Year after year, paper after paper, the two numbers stayed stubbornly apart. The Hubble tension, as it came to be called, grew from a curiosity into one of the biggest unsolved puzzles in all of modern physics. Some physicists started wondering if the tension was not a mistake at all. What if the two methods were both right, and the universe itself was the thing that did not match? Now look at the tension through the lens of changing dark energy. This is where it clicks. If the push was stronger in the early universe and weaker today, then the expansion rate was different at different moments in cosmic history. The method that reads the ancient light is measuring a universe where the push was at full strength. The method that looks at nearby galaxies is measuring a universe where the push has already faded. Two methods, two eras, two different push strengths, two different answers. Of course they disagree. A changing dark energy does not just explain why the numbers are off. It explains why they had to be off. The tension was never a bug. It was a fingerprint left by a force that was changing over time. A clue that had been sitting in the data for over a decade, waiting for someone to read it the right way. That is the kind of moment that keeps a physicist awake. When two separate mysteries point at the same answer, the odds that both are coincidences drop sharply. The ground starts to shift. The grip was always loosening. We just could not feel it until now. The atoms in your hand right now were shaped by a force that was stronger when they were made than it is tonight. The iron in your blood was forged inside a star that burned under a fiercer push. The calcium in your bones condensed from a cloud that gravity pulled together against a headwind that has been dying ever since. You are a product of a fading push, and so is everything you have ever seen, touched, or loved. A graduate student on the DESI team was running routine checks on a data pipeline late one night. It was the kind of work nobody notices. Scanning logs. Comparing outputs, looking for errors that would be invisible to anyone who had not stared at the same numbers for months. Then she spotted something. The numbers for the early universe did not line up with the expected trend. The W parameter was not sitting where the model said it should for that era. She flagged it. Her supervisor told her to rerun the analysis. She reran it 4 times. Different settings. Different software. The trend held every time. That flag became a key section in the most important cosmology paper of the decade. Not a dramatic discovery on a mountaintop. Not a shouting match at a conference. Just a quiet voice at 2 a.m. saying, "That does not look right," followed by weeks of careful checking, followed by the slow, terrifying realization that the quiet flag was pointing at something enormous. The theoretical candidates for what dark energy might be, if it is not a constant, come in 3 flavors. None of them are comfortable. Each one comes with a price. First, quintessence. We talked about this earlier. A slow rolling energy field that fills all of space and weakens over time, like a fog burning off as the morning warms. At dawn, the fog is thick. You can barely see the road. By noon, it has thinned to wisps. By evening, it is gone. What makes quintessence appealing to physicists is that it is testable. If dark energy is a dynamic field instead of a constant, it should leave specific fingerprints in the data, particular patterns in how the expansion rate changes across different eras, particular signatures in the clustering of galaxies. DESI's data is not precise enough yet to confirm quintessence beyond doubt, but it is precise enough to make it a serious candidate for the first time in history. The math works. The models fit the DESI data reasonably well, and quintessence has one more advantage: it is tame. Strange, absolutely. The idea that the whole universe is soaked in a slow-dying energy field is not easy to accept. But it is the kind of strange that equations can describe, the kind that gives physicists something to test, something to calculate, and something to argue about at conferences with real numbers on the whiteboard instead of helpless shrugs. Second, phantom energy, the dangerous option. Phantom energy is a field where the push does not fade. It grows, gets stronger every era. Imagine filling a bathtub with the drain sealed shut and the faucet jammed on. The water rises, no overflow valve, no shutoff, just more pressure, more volume, year after billion years until the porcelain cracks. DESI's current data leans toward weakening, not strengthening. That argues against phantom energy right now. But the error bars are still wide enough that phantom energy has not been ruled out completely. It sits at the edge of the allowed zone like a shape in the corner of your eye. Turn to look at it, and it seems to vanish. Look away, and there it is again. If phantom energy is real, the universe ends in a big rip. We covered that. Every structure torn apart. Nobody wants that to be the answer, but nobody has proven it impossible either. Third, and this is the idea that makes some physicists nervous in a completely different way. Maybe dark energy does not exist at all. Maybe there is no invisible force pushing the universe apart. Maybe the problem is not with the cosmos. Maybe the problem is with our theory of gravity. Einstein's general relativity works at every scale we have tested: planets orbiting stars, moons orbiting planets, satellites circling Earth, even 2 black holes smashing together a billion light years away, sending waves rippling through the fabric of space. All confirmed, all precise. But nobody has tested gravity at the scale of the entire visible universe. No experiment can. The distances are too vast, the timescales are too long, the measurements are too indirect. If gravity behaves even slightly differently at the cosmic scale, the acceleration we see might not need an extra push at all. The effect we have been calling dark energy could be a shadow on the wall, a misreading of how gravity actually works when you zoom all the way out. This idea is called modified gravity. It is unpopular. Not because the math fails. The math works fine. Several versions of modified gravity can match the same observations. The reason it is unpopular is that it means rewriting the most celebrated theory in the history of physics. It means looking at general relativity, the theory that predicted black holes before anyone found one, and saying it needs a correction at the largest scales. Some physicists refuse to consider it, others quietly work on it in private. Nobody wants to be the person who calls Einstein incomplete unless the data leaves no other door open. But the data is getting harder to ignore. And if DESI's drift holds up over the next few years, the modified gravity camp will get much louder. What comes next will settle it, or at least narrow the options down to a fight between 2 instead of 3. DESI is still scanning. Every night, as the sun drops below the Arizona horizon and the dome opens, 5,000 robot eyes lock onto fresh galaxies. They read the light, they log the distance, they move to the next batch. By the time the full survey finishes in a few years, it will have catalogued over 40 million galaxies, 40 million tiny windows into the past, each one carrying a piece of the expansion story that no human eye could read without help. That is not a number you hear and move on from. 40 million galaxies means 40 million independent measurements of how fast the universe was growing at that particular moment in time. Stack them together and you get a record of the expansion that is 10 times more detailed than anything that existed 5 years ago. And DESI is not working alone. The Euclid Space Telescope, launched by the European Space Agency in 2023, is already in orbit. It floats above the atmosphere, above the clouds, above every source of light and heat that blurs the view from the ground, a clean, silent eye pointed at the deep cosmos. What Euclid measures is subtle but powerful. It reads the shapes of distant galaxies, not their colour, not their brightness, their shape. When light from a faraway galaxy passes through expanding space, the expansion warps the image slightly, like looking at your reflection in a spoon. Almost correct, but bent just enough that a precise instrument can measure the bending. By reading those tiny distortions across millions of galaxies at different distances, Euclid maps how dark energy shaped the growth of cosmic structure over time. Each slice of distance is a different era. Each distortion is a record of how hard the push was shoving at that moment. Stack them together and you get a second, independent expansion history, a cross-check on everything DESI found. And then there is the Nancy Grace Roman Space Telescope, coming soon. Named after the woman who fought to build Hubble when nobody in the government wanted to pay for it, Roman will carry a field of view 100 times wider than Hubble, capturing more sky in a single image than any space telescope before it. Different wavelengths, deeper reach, more galaxies per frame. Between DESI on the ground, Euclid in orbit, and Roman on the way, the next decade will produce more data about dark energy than the previous 50 years combined. That is not an estimate. It is a count based on the instruments already built and already collecting light. That data will do one of two things. Either it confirms that dark energy is truly changing, that the cosmological constant was wrong from the start, and that physics enters a new era with more questions than answers. Or it reveals that the drift was a statistical shadow, lambda was constant all along, and the standard model earns another generation of trust. Either way, the question has been asked. In science, once a question this large is on the table, it does not leave. The instruments are running, the data is flowing, and somewhere inside the numbers, buried in the light of galaxies that burned out before the Earth was born, the answer is already there. Waiting, one of the lead DESI scientists said something in a press briefing that stuck with everyone in the room. She said she felt like someone who had been reading the same book for 25 years and had just reached a chapter written in a language she did not speak. The story was not over. She just could not read the ending yet. There is a weight to that admission. For a generation, cosmologists have been telling the public a confident story. The universe will expand forever. The stars will burn out. Everything ends in cold silence. It was sad, but it was solid.